Welcome, ICT Level 6 students. Today, we're building your foundation in database management systems. Now, we're going to treat this explainer as a true first principles masterclass designed specifically to get you ready for your 2026 industry careers. My goal today isn't just to throw a bunch of textbook definitions at you. No, it's to elevate you from being a basic coder to a systems engineer, someone who actually understands how to guarantee security, integrity, and performance in real-world ICT environments.
Okay, here's our game plan for today. We've got 1. The problem, 2. Core myths, 3. MySQL mechanisms, 4. Industry scenarios, 5. Key-vet assessments, and finally, 6. Future topics and summary. This is structured specifically to bridge the theory with the actual practical skills you're going to need. Let's dive right in.
Before we even think about touching a single line of code, we really need to ask the most important engineering question out there. What problem does this concept actually solve? I mean, to understand a database management system, we first have to understand the absolute chaos that exists without one.
So, Section 1, the problem. Let's take a look at the world before databases existed.
Okay, picture this. You get hired tomorrow, right? Your job is to build the back end for a SACO with 5,000 members, or maybe a hospital with 200 daily admissions, or a college with 3,000 students. But here's the catch. You're told no MySQL, no PostgreSQL, absolutely no Oracle. You only have a basic computer file system and your programming language, just files and code. If that's all you have, your organization has to manually solve some incredibly complex storage and recovery problems completely from scratch. Believe it or not, before 1970, this was genuinely how computing worked. Every single company was reinventing the wheel, and honestly, usually getting it catastrophically wrong.
And you know, that brilliantly illustrates exactly why the DBMS was invented in the first place. A DBMS exists fundamentally as a shared engineering solution to make 4 specific system failures structurally impossible at any scale. First up, storage and retrieval. How do you find data fast without scanning every single file line by line? Second, data integrity. How do you stop bad or corrupted data from being saved? Third is security authorization. How do you control who sees what? And fourth, concurrency control. How do you stop 2 programs from overwriting each other's data at the exact same millisecond? A DBMS is purpose-built software, and its entire job is to handle these 4 failures perfectly, once for everyone.
All right, moving on to Section 2, Core Myths. Let's clear up a few common misconceptions right now.
The most crucial difference you need to understand is between a database and a DBMS. You'd be surprised how often students get this wrong. A database is the organized, structured collection of related data. It is the data itself. A DBMS, like MySQL or PostgreSQL, well, that's the software engine that creates, manages, and secures that data. So remember, MySQL is not your database. MySQL is the engine running it. Another major distinction is schema versus instance. Think of your schema as the blueprint. It's the table structure, the data types, the constraints. It almost never changes day to day. The instance, on the other hand, is the actual data living in the system at a given moment in time, and that changes constantly as users click around and interact. Knowing the difference between your static architecture and your dynamic data is absolutely critical for any systems engineer.
Which brings us to Section 3, MySQL mechanisms. Let's look under the hood.
What's really fascinating here is how every abstract concept we just talked about translates directly into a tangible MySQL mechanism. For storage, MySQL uses B-tree indexes, so a 50 million row table can snap back results in milliseconds. For integrity, it uses constraints, like not null or foreign key, to just flat out reject bad writes before they ever hit the disk. For security, you've got grant and revoke commands to attach specific permissions to specific users. And for concurrency, MySQL's InnoDB engine uses MVCC, that's multi-version concurrency control, which basically allows readers to see a consistent snapshot of the data while writers do their thing, entirely stopping those silent data overwrites.
And to maintain what we call ACID properties, that's atomicity, consistency, isolation, and durability. You wrap your operations in a transaction. You begin with start transaction. Then you perform your updates. Finally, you either commit if everything went perfectly, or you roll back if a failure pops up. It's all or nothing. Everything completely succeeds, or it fully rolls back. This is your formal, mechanical fix for data corruption, and it's guaranteed by something called the write-ahead log, which ensures that even if someone literally pulls the power cord out of the wall, your data recovers perfectly.
Okay, Section 4, Industry Scenarios. Let's ground this in reality.
Let's look at what happens in real Kenyan industry systems if these concepts are misunderstood. If a hospital system you maintain misunderstands atomic transactions, you could face a catastrophic operational hazard. A patient is admitted into the system, but the bed assignment part of the code fails, leaving them standing there with no bed. Or in a SACO, imagine dispersing a massive loan to a member, but the ledger update fails. The money is literally gone, but the database says it isn't. ACID transactions ensure all these steps happen together, or they don't happen at all.
It's the same story everywhere. In a school system, enrolling a student without atomically updating their fee balance means students are sitting in class with zero billing record. In a bank, without row-level locking, two tellers could update the exact same account at the exact same time, and boom, money vanishes into thin air. Even in an e-commerce checkout, concurrent customers might try to buy the exact same single item left in stock. The DBMS handles the locking so you don't have to leave your data integrity up to pure chance.
Moving to Section 5, TVET assessments, because this is going to be on the test.
Listen, this isn't just theory. It directly impacts your TVET CDAC certification and your overall industry readiness. As part of your ICT Technician Level 6 standard, managing a computerized database system is a core unit. For your 40% summative assessment, you must demonstrate practical competence here. You'll be required to design, create, manipulate, and maintain these databases. That means practically applying everything we've just discussed, setting up those B-tree indexes, writing the actual queries, and heavily focusing on security using tools like Grant and Revoke. Ultimately, you're being trained to be trusted with an organization's most valuable asset, their data.
Let's wrap things up with Section 6, Future Topics and Summary.
Looking ahead to our future sessions, we'll be diving into the 3-schema architecture. You have the internal schema, the physical reality of how things sit on the hard disk, the conceptual schema, your logical tables and rules, and the external schema, the customized views your application actually sees. This specific architecture provides something called data independence. What that means for you in 2026 is that you can tune your physical storage performance, add indexes, or completely upgrade the hardware at the internal level without having to rewrite a single line of your application code at the external level. That is exactly what makes databases maintainable over a 10 or even 20-year lifespan.
So, to quickly summarize today's session, a DBMS prevents the 4 critical failure classes: storage, integrity, security, and concurrency. It relies on brilliant internal mechanisms like ACID transactions, row-level locking, and write-ahead logs to enable the secure, highly concurrent enterprise systems used in our hospitals, banks, and schools. Mastering these first principles is the key. It elevates you from someone who just writes a few SQL queries into a true systems engineer who can guarantee the survival of an organization's daily operations.
Before we move on to database models in our next session, I want to leave you with a practical question. Think about the local apps you use every single day here in Kenya. If they suddenly lacked a DBMS tomorrow, which of the 4 failure classes, storage, integrity, security, or concurrency, do you think would cause the most immediate, unignorable chaos in your life? Really think about that. Go get your hands dirty in the MySQL engine room, and I'll see you in the next explainer.